Comets have always captivated human imagination, appearing in the night sky as brilliant, otherworldly streaks of light that travel through the vast reaches of space. To truly understand these enigmatic visitors, we must journey back to their origins, a story that begins some 4.6 billion years ago, in the very cradle of our solar system. Comets are among the oldest objects in our solar system, born from the primordial dust and gas cloud that surrounded the young sun. This cloud, known as the solar nebula, was a chaotic mix of particles, gas, and ice that eventually coalesced into the planets, moons, and smaller celestial bodies. Amidst this formation frenzy, countless tiny fragments, composed mainly of rock, dust, and ice, were left over. These remnants, untouched by the processes that formed the planets, became the comets we know today. Most comets originate from two primary regions at the solar system's edge, the Kuiper belt and the Oort cloud. The Kuiper belt is a vast ring of icy bodies, including dwarf planets like Pluto, located just beyond the orbit of Neptune. Here, comets typically have relatively short orbits, taking less than 200 years to complete a trip around the Sun. In contrast, the Oort cloud is an immense, spherical shell of icy debris that envelops the solar system at distances up to a light-year away. Comets from this region, known as long-period comets, can take thousands or even millions of years to complete their orbits. Despite their distant homes, comets can find themselves drawn into the inner solar system. Gravitational disturbances, often caused by passing stars or the giant planets like Jupiter and Saturn, can nudge a comet from its stable orbit, sending it hurtling towards the Sun. This journey marks the beginning of a dramatic transformation, as the comet transitions from a frozen, dormant body into a radiant, active traveler. At their core, comets are composed of a mixture of water ice, frozen gases like carbon dioxide, methane, and ammonia, and tiny grains of rock and organic materials. This unique blend of elements has earned comets the nickname, dirty snowballs, but they are far more complex than this term suggests. Their nuclei, which are usually only a few kilometers across, are dark and irregularly shaped, often coated with a layer of soot-like material that helps protect the fragile ice within from the heat of the Sun. Scientists believe that this coating is made of complex organic compounds, formed by the interaction of ultraviolet radiation from the Sun with the ices and gases on the comet's surface. These compounds may hold the keys to understanding the building blocks of life itself. In many ways, comets are like cosmic time capsules, preserving the chemical signatures of the solar nebula from which they were born. When a comet begins its journey toward the Sun, it enters a phase of rapid change. The increasing heat causes the ices within its nucleus to sublimate, transforming directly from a solid state to a gas. This process releases trapped gases and dust, creating a glowing, ephemeral atmosphere around the nucleus called the coma. For a comet nearing the Sun, the coma can expand to a size greater than that of Earth, creating a stunning sight visible even from millions of kilometers away. The most spectacular feature of a comet is its tail, which emerges as the coma interacts with the solar wind, a continuous stream of charged particles flowing outward from the Sun. This interaction creates two distinct tails, a dust tail and an ion tail. The dust tail is formed from small solid particles released from the nucleus. It is pushed outward by the pressure of sunlight and typically appears as a broad, curved streak. Meanwhile, the ion tail is made up of charged particles created by the solar wind's interaction with the comet's gases. It forms a narrow, straight tail that always points directly away from the Sun. These tails can stretch for millions of kilometers, making comets some of the longest structures in the solar system. The tail's formation is a dynamic and ever-changing process, shaped by the Sun's heat, the solar wind's strength, and the comet's own rotation and activity. No two comets are exactly alike. Each has a unique character and display, influenced by its composition, size, and distance from the Sun. The journey of a comet is a delicate balance between competing forces. As it moves closer to the Sun, the comet's nucleus is heated more intensely, causing increased sublimation and often violent outbursts of gas and dust. These outbursts can create jets that push the comet in unpredictable directions, altering its trajectory and sometimes even fragmenting it into pieces. Despite this volatility, some comets manage to survive multiple trips around the Sun, becoming periodic visitors to our inner solar system. For example, Halley's Comet, perhaps the most famous of all, completes an orbit every 76 years, while Comet Encke, with an orbit of just 3.3 years, is the most frequent visitor. Other comets, like Comet Hale-Bopp, only appear once in thousands of years, offering a rare glimpse of the grandeur to human eyes. A comet's fate is as unpredictable as its journey. Some are drawn into the sun's gravitational embrace, disintegrating in a final, fiery plunge. Others may collide with a planet or moon, leaving a visible scar, like the comet Shoemaker-Levy 9, which spectacularly impacted Jupiter in 1994. Many comets simply fade away, their ice is gradually vaporized by repeated close passes to the sun until only a trail of rocky debris remains. However, even in death, comets leave their mark on the cosmos. The debris left by disintegrating comets can form meteor showers when Earth passes through their remnants. Each summer, the Perseid meteor shower, one of the most famous, lights up our skies, a legacy of the comet Swift-Tuttle. As these cosmic wanderers travel through space, they continue to serve as messengers from the outer solar system, carrying with them clues about the dawn of our solar neighborhood. The secrets they hold about the early solar system's formation, evolution, and perhaps even the origins of life make them invaluable to scientists and space explorers. Their journeys are far from over. Each comet that graces our skies brings with it new mysteries to be unraveled and new wonders to behold. Comets, while appearing as fleeting streaks of light in our skies, are complex celestial bodies with distinct parts that each tell a different story of their journey through space. To truly understand the anatomy of a comet, we must explore its three main components: the nucleus, the coma, and the tail. Each of these elements plays a critical role in the life of a comet, contributing to the dynamic display we witness when a comet graces the inner solar system. At the core of every comet lies the nucleus, the small, solid body that serves as the heart of the comet. Nuclei are typically a few kilometers across, though some can be larger or smaller. Despite their size, these nuclei are incredibly diverse in their composition and structure. Made primarily of ice, dust, rock, and organic compounds, they are often described as dirty snowballs, but this simple description fails to capture the true complexity. Recent missions like the European Space Agency's Rosetta, which closely studied Comet 67P, Churyumov-Gerasimenko, have revealed that cometary nuclei are irregularly shaped, with rugged surfaces covered in pits, cliffs, boulders, and depressions. These features are the result of a long history of activity and transformation, shaped by the sublimation of ices and the violent outgassing that occurs as the comet nears the Sun. The surface of the nucleus is often covered with a dark, crust-like layer of organic-rich material that forms as ultraviolet radiation from the Sun breaks down simpler molecules into more complex organic compounds. This layer acts as an insulator, protecting the fragile ice within from the Sun's heat. However, beneath this crust, the interior is still largely frozen, composed of water ice mixed with other volatile substances like carbon dioxide, methane, and ammonia. These ices are ancient, having remained unchanged since the solar system's formation. The nucleus also contains trapped gases that have been sealed in its ice for billions of years. When the comet approaches the Sun, the heat causes these gases to expand and escape, carrying dust particles with them and creating jets that can dramatically alter the comet's rotation and path. The shape and rotation of the nucleus affect how and where these jets emerge, leading to a variety of dynamic behaviors that make each comet unique. As a comet travels closer to the Sun, the nucleus begins to warm up, and the ices within it start to sublimate, transitioning directly from a solid to a gaseous state. This process releases not only gases but also fine dust particles trapped within the ice. The result is the formation of the coma, a vast, glowing envelope of gas and dust that surrounds the nucleus. The coma is often the most visible part of a comet, appearing as a bright, fuzzy ball in the night sky. It can grow to be immense in size, sometimes spanning hundreds of thousands of kilometers, dwarfing the nucleus itself. Despite its size, the coma is extremely tenuous, with densities lower than the best laboratory vacuums on Earth. Its glow comes from the interaction of sunlight with the gas and dust particles. Sunlight reflects off the dust, while ultraviolet light ionizes some of the gases, causing them to emit light. The composition of the coma can provide a wealth of information about the comet. For instance, water vapor, carbon dioxide, carbon monoxide, and ammonia are some of the most common gases detected in cometary comas. Scientists use spectrometry to analyze the light emitted or absorbed by the coma to determine the specific elements and compounds present. giving insight into the chemical makeup of the comet and, by extension, the early solar system. Interestingly, the coma is not uniform. As the nucleus rotates, jets of gas and dust can burst from localized areas on its surface, creating bright spots or streaks within the coma. These jets can even cause the nucleus to spin faster or slower, further influencing the shape and structure of the coma. Occasionally, a comet may experience a dramatic outburst, where a sudden increase in activity causes the coma to expand rapidly, sometimes increasing in brightness by several orders of magnitude. The most dramatic feature of a comet, and perhaps the most iconic, is its tail. Contrary to common belief, a comet does not have just one tail but often two, a dust tail and an ion tail, each formed through different processes and displaying different behaviors. 1. The dust tail. The dust tail is formed from tiny, solid particles that were embedded in the comet's nucleus and released as the ices sublimate. These particles are pushed away from the sun by the pressure of sunlight, which exerts a gentle force on the dust grains, causing them to drift away from the nucleus. The dust tail typically appears as a broad, curved, and glowing white or yellow streak, reflecting sunlight like a trail of breadcrumbs marking the comet's path. The shape of the dust tail is influenced by the comet's movement and the solar wind. As the comet swings around the sun, the dust particles, which are relatively heavy, lag behind, creating a curved tail that can stretch millions of kilometers. The size and brightness of the dust tail depend on the amount of dust released and the intensity of the solar radiation. Because the dust particles are small, they scatter sunlight in all directions, making the tail visible even from Earth. 2. The ion tail. The ion tail is composed of gases that have been ionized by the sun's ultraviolet radiation. When molecules in the coma are ionized, they become charged and interact with the solar wind, a stream of charged particles emitted by the sun. This interaction creates an electric field that sweeps the ions away from the sun at high speeds, forming a narrow, straight tail that always points directly away from the sun. The ion tail often appears blue or green due to the presence of specific ionized gases, such as carbon monoxide or diatomic carbon, C2, which emit light at certain wavelengths when they are excited. The ion tail is highly dynamic, constantly changing in shape and structure as it is affected by the solar wind's variations in speed and density. Sometimes, the tail can break apart or form kinks and twists, creating a mesmerizing display of light and motion. The formation and behavior of a comet's coma and tails are driven by its interaction with the sun. The sun's heat causes the sublimation of ices, creating the coma, while the solar wind and radiation pressure shape and direct the tails. This interaction is a delicate dance of forces, balancing the pull of gravity, the push of solar radiation, and the streams of charged particles from the sun. As a comet approaches perihelion, the point in its orbit closest to the sun, its activity peaks. The sublimation rate increases, the coma expands, and the tails grow longer and brighter. This is when comets are at their most spectacular, often visible to the naked eye from Earth. However, this period of maximum activity is also when comets are most vulnerable. The intense solar heat can cause the nucleus to crack or even fragment, leading to dramatic changes in the comet's appearance and sometimes to its complete disintegration. No two comets are exactly alike, and each exhibits its own unique characteristics. Factors such as the comet's size, composition, rotation, and distance from the sun all play a role in determining its behavior and appearance. Some comets, like Halley's Comet, have well-defined orbits and return at predictable intervals, allowing us to study them over many centuries. Others, like Comet Hale-Bopp, make a single, unforgettable appearance before retreating to the far reaches of the solar system, not to return for thousands of years. Comets can also surprise us with their sudden changes. A once dim comet might suddenly brighten, while a comet expected to put on a great show may fizzle out, breaking apart or losing its activity prematurely. These unpredictable behaviors make comets a constant source of intrigue and a reminder of the dynamic and ever-changing nature of our solar system. Chapter 3, The Dance of Discovery. Humanity's fascination with comets throughout history. Comets have been both feared and revered, appearing in the night sky as sudden, brilliant guests that seem to defy the predictable order of the heavens. Ancient civilizations, astronomers, and mystics have all gazed at these celestial wanderers with wonder, apprehension, and curiosity. To understand how comets have shaped human thought, we must travel through time, from ancient interpretations of these enigmatic objects to the cutting-edge discoveries of modern science. For much of human history, comets were viewed with a mix of awe and fear. Unlike the stars, planets, and moon, whose movements could be charted and predicted, comets appeared unpredictably, often with dramatic, fiery tails that stretched across the sky. Ancient societies saw these sudden appearances as signs from the gods, messengers of divine will, or harbingers of significant events. In Mesopotamia, the earliest known records of comets date back to 2300 BCE, where they were seen as portents of doom. The ancient Sumerians and Babylonians, skilled in astronomy and astrology, meticulously recorded the appearances of comets, believing they foretold disasters such as plagues, wars, or the death of kings. In their understanding, comets were unpredictable visitors from the celestial realm, intruding upon the orderly movements of the stars. The Chinese, too, paid close attention to comets, and their records are among the most detailed and oldest in existence. Chinese astronomers, who had a profound interest in celestial phenomena, meticulously catalogued the appearances of comets, noting the direction, color, and shape. They described comets as broom stars, sweeping the heavens clean, and often viewed them as omens, signaling shifts in the balance of power or significant events in the empire. These records, spanning thousands of years, provide valuable data for modern scientists studying the orbits and behavior of ancient comets. In Europe, comets were long regarded with fear and superstition. For centuries, they were seen as divine warnings or messages of impending doom. One of the most famous examples of this belief is the appearance of Halley's Comet in 1066. Its bright, spectacular appearance in the sky was seen as an ominous sign, coinciding with the death of the English King Edward the Confessor and the subsequent invasion of England by William the Conqueror. The comet is even depicted in the Bayeux Tapestry, a historical artifact that illustrates the events leading up to the Norman conquest of England. The perception of comets began to shift dramatically during the Renaissance and the scientific revolution. As scientific inquiry and observation became more rigorous, thinkers like Tycho Brahe, Johannes Kepler, and Isaac Newton began to challenge the long-held views of comets as supernatural omens. They sought to understand these celestial bodies through mathematics, observation, and reason. In 1577, Tycho Brahe, a Danish astronomer, made meticulous observations of a bright comet that appeared in the night sky. By comparing observations made from different locations, Brahe concluded that the comet was not an atmospheric phenomenon, as previously thought, but a celestial object moving through the space between planets. This was a revolutionary idea that challenged the Aristotelian view that the heavens were unchanging and perfect. Johannes Kepler, Brahe's assistant, also studied comets intensely. Although he was unable to fully explain their orbits, he proposed that comets moved along straight paths through space. However, it was Isaac Newton who ultimately provided a comprehensive explanation. In his landmark work, Principia Mathematica, published in 1687, Newton demonstrated that comets followed elliptical orbits around the Sun, governed by the same gravitational laws that dictate planetary motion. This insight not only demystified comets but also integrated them into the larger framework of celestial mechanics. Newton's work paved the way for Edmund Halley, a British astronomer, to make one of the most significant breakthroughs in the study of comets. Using Newton's laws of motion, Halley calculated the orbits of several comets recorded in historical accounts and noticed that a particular comet seemed to return approximately every 76 years. He predicted its return in 1758, and when it did, the comet was named in his honor, Halley's Comet. This marked the first time a comet's return had been accurately predicted, transforming comets from mysterious wanderers into predictable celestial bodies. The 20th and 21st centuries have seen an explosion in comet research, driven by advances in technology and a growing understanding of the solar system. Ground-based telescopes, space probes, and computer modeling have allowed scientists to study comets in unprecedented detail, revealing new insights into their composition, behavior, and significance. One of the first significant missions to study a comet up close was NASA's International Cometary Explorer, ICE, which in 1985 flew through the plasma tail of Comet Giacobini-Zinner, gathering valuable data about the composition of the comet's tail and its interaction with the solar wind. This was followed by the Giotto mission in 1986, which made a historic close encounter with Halley's Comet, capturing the first ever images of a comet's nucleus and revealing a dark, rugged surface spewing jets of gas and dust. In 2004, the European Space Agency launched the Rosetta mission, which aimed to orbit and land on a comet for the first time. After a decade-long journey through space, Rosetta arrived at Comet 67P, Churyumov-Gerasimenko in 2014. The mission's Philae lander successfully touched down on the comet's surface, despite some challenges, and conducted groundbreaking experiments. Rosetta provided detailed images of the comet's surface, revealing its complex landscape and shedding light on its composition, structure, and activity. Rosetta's data confirmed that comets contain a variety of organic compounds, including some of the essential building blocks for life, such as amino acids. This discovery supports the theory that comets may have played a crucial role in delivering water and organic materials to the early Earth, potentially jump-starting the processes that led to life. While scientific understanding of comets has grown, the cultural significance has not diminished. Comets have continued to inspire awe, wonder, and curiosity in people around the world. In literature, art, and film, comets often serve as metaphors for change, transformation, and the unknown. They are portrayed as harbingers of both destruction and renewal, capable of bringing about apocalyptic scenarios or heralding new beginnings. In literature, comets have been used to symbolize sudden, dramatic change. For example, in Samuel Clemens' Mark Twain's autobiography, he famously linked his life to Halley's Comet, noting that he was born in 1835, the year Halley's Comet was visible, and predicted that he would die with its return in 1910, a prediction that proved true. Twain's life, like the comet, seemed to embody the unpredictability and brilliance associated with these celestial events. In popular culture, comets often feature in science fiction and fantasy. From apocalyptic movies where a comet threatens to destroy Earth, to more imaginative tales where comets are carriers of life or alien technology, they continue to serve as symbols of cosmic mystery and intrigue. These stories tap into our fascination with the unknown and our desire to explore the universe. As we look to the future, the study of comets promises to reveal even more about the origins of our solar system and the potential for life beyond Earth. Upcoming missions, such as the European Space Agency's Comet Interceptor, aim to explore new, untouched comets that are entering the inner solar system for the first time. By capturing detailed data from these pristine bodies, scientists hope to gain a deeper understanding of the primordial materials that existed at the dawn of the solar system. Additionally, new telescope technologies and advances in artificial intelligence will allow for more precise tracking and analysis of cometary movements and compositions. Ground-based observatories, like the Vera C. Rubin Observatory in Chile, are expected to revolutionize our ability to detect and study comets, potentially uncovering thousands of new objects and providing real-time data on their behavior. There is also increasing interest in mining comets for their resources. As humanity begins to consider the feasibility of deep space exploration and colonization, comets, rich in water ice and other valuable materials, could serve as crucial waypoints or refueling stations. Extracting resources from comets could pave the way for sustainable space travel, enabling missions to Mars, the outer planets, and beyond. Comets are often referred to as cosmic messengers, because they offer invaluable clues to the origins of our solar system and, potentially, the beginnings of life on Earth. As we explore these celestial bodies, we begin to see them not merely as frozen relics from the dawn of time but as dynamic agents that may have played a crucial role in shaping our world. Comets formed over 4.6 billion years ago from the same primordial dust and gas cloud that birthed our Sun and planets. While planets and moons have undergone significant changes due to geological processes, comets have remained largely unchanged, preserving the original ingredients from that era. This makes them perfect time capsules that contain the building blocks of our solar system's earliest days. When comets approach the Sun, their icy surfaces begin to vaporize, releasing gases and dust. This process creates their spectacular tails but also exposes their internal composition to analysis. Observations and missions, like Rosetta's to Comet 67P, have shown that comets contain a range of organic molecules, including amino acids, which are the basic building blocks of proteins and life as we know it. This discovery supports the hypothesis that comets may have contributed to the chemical complexity required for life on Earth. The idea that comets could be carriers of life is not new. The Panspermia hypothesis suggests that life, or at least the precursors of life, may have originated elsewhere in the cosmos and been transported to Earth via comets, asteroids, or meteorites. Comets, with their abundant water ice and organic compounds, are considered prime candidates for this role. According to this theory, comets could have brought essential organic molecules, water, and even simple microorganisms to Earth during the period known as the Late Heavy Bombardment, around 3.8 billion years ago. This period was characterized by frequent and intense comet and asteroid impacts. If comets deposited these materials in Earth's early oceans, they might have provided the raw ingredients for the development of life. Although the Panspermia hypothesis remains speculative, the discovery of complex organic compounds on comets lends it some credibility. Missions like NASA's Stardust, which collected and returned dust samples from Comet Wild 2, found glycine, an amino acid used by living organisms. This discovery hints at a tantalizing possibility that the fundamental components of life might be widespread throughout the universe, waiting to spark life wherever conditions allow. Another theory suggests that comets played a significant role in delivering water to Earth. The early Earth was likely a hot, molten place, and any original water might have evaporated or been lost to space. As the planet cooled, it is believed that comets and water-rich asteroids could have bombarded the Earth, replenishing its oceans. Studies of cometary water, like those from the Rosetta mission, reveal that the water in some comets has a different deuterium to hydrogen ratio than Earth's oceans. This suggests that while some comets might have contributed to Earth's water supply, they are unlikely to be the sole source. Nonetheless, comets remain a fascinating possibility in the quest to understand where Earth's water, and perhaps life, originated. As we peer into the future, comet exploration stands on the cusp of remarkable advances. With each new discovery, we gain a deeper understanding of these celestial wanderers, their significance to our solar system's history, and the potential role in the future of space exploration and resource utilization. Several exciting comet missions are on the horizon. One of the most anticipated is the European Space Agency's ESA Comet Interceptor mission, planned for launch in the late 2020s. Unlike previous missions targeting known comets, the Comet Interceptor aims to position itself at a stable point in space, ready to intercept a yet-to-be-discovered comet. The hope is to study a new comet, one that has never visited the inner solar system and is therefore pristine and unaltered. This mission could provide unprecedented insights into the primordial materials that existed before the solar system formed. Another upcoming mission is NASA's CESAR, Comet Astrobiology Exploration Sample Return, which aims to return samples from Comet 67P, Churyumov-Gerasimenko, the same comet visited by Rosetta. CESAR intends to bring back samples of the comet's surface material, enabling scientists to study its composition in detail on Earth, using tools far more sophisticated than those that can be sent into space. The analysis of these samples could offer new clues about the role of comets in delivering the ingredients necessary for life. As humanity contemplates a future of deeper space exploration, the concept of comet mining is gaining traction. Comets, with their abundant reserves of water ice, carbon-based molecules, and rare metals, represent a potential goldmine for future explorers and colonists. Water, in particular, is a valuable resource, not only for sustaining life but also because it can be broken down into hydrogen and oxygen to create rocket fuel. Mining comets could provide the raw materials needed for long-duration space missions or even the establishment of outposts on the Moon, Mars, or beyond. However, the challenges are immense. Capturing and mining a comet, with its irregular shape, unpredictable outgassing, and weak gravity, poses significant technical and logistical difficulties. New technologies and approaches, such as advanced robotics, autonomous spacecraft, and AI-driven systems, will be essential to turn the concept into reality. Comets will continue to play a crucial role in the search for life beyond Earth. By studying comets in our solar system, scientists hope to gain a better understanding of how organic molecules are distributed across space and how they may have contributed to the emergence of life on other planets or moons. Future missions may target the outer solar system's giant comets or centaurs, objects that share characteristics of both comets and asteroids, to explore their composition and search for signs of prebiotic chemistry. Instruments designed to detect complex organic molecules, analyze isotopic ratios, and map the surfaces of these objects in detail could reveal whether the conditions that fostered life on Earth might exist elsewhere. Ultimately, our fascination with comets is driven by a profound sense of curiosity and wonder. They are reminders of the mysteries that still lie beyond our reach, questions that challenge our understanding of the universe and our place within it. As we continue to explore comets, we are not only seeking answers to fundamental scientific questions but also fulfilling a deeply human desire to explore the unknown.